So myself, Dr. K. Saktimurgan, Associate Professor, Department of BC, PSNCET College of Engineering and Technology, Tirunelveli. My topic is design of logic gates using pass transistor. So by using a pass transistor, we have to design a logic gates. So logic gates means AND gate, NAND gate, OR gate, NOR gate, XOR gate, XNOR gate. Okay. Now we will see one by one how to design AND gate by using a pass transistor. So first one, design of AND gate using pass transistor logic. So now, so here there is a AND gate truth table. When there is a 2 input AND gate, when both input are 0, output is 0, and any one of the input is 0, another one is high, the output will be 0, and same concept, another A is high, output B is low, the output will be 0, both will be high, output will be 1. Now before designing a pass transistor, what is meant by pass transistor? So pass transistor is nothing but passing the information or data from input to output. So here number of transistors will be reduces compared with the other logic and all. So when you reduce the number of transistors, definitely the speed will be increases, delay will be decreases, proportionately the speed power consumption also less. So our main VLSI objective is you have to minimize the less power consumption, and speed also we have to increase. So if we increase number of transistors, definitely the speed will be decreases. So this is the concept as well as by using a pass transistor now we have to design. So here see the diagram. When AB, there is a here there is a pass transistor, NMOS transistor and NMOS transistor. So this is nothing but a B is nothing but a control input, and A is nothing but a data input. So we taken B as a control input and A as a data input. Now see here B is equal to 0, again here B is equal to 0. So both inputs are 0. Now we will check the data input. Data input, when A is equal to 0, what about the output? Here it is 0. And here A is equal to 1, the output will be 0. Now irrelevant of input, that means when 0, output will be 0, 1, output will be 0. So now we have to assign. So B is nothing but control input, we have to assign as B bar. So B is equal to 0 means nothing but B bar. So when we assign a B is equal to 0, so here see this, B is equal to 0. So now when it is 0, whatever input will be, the data input will be transferred to the output. So here I am explaining deeply. When B is equal to 1, top transistor on, that is B means control input. When B is equal to 0, bottom transistor on. So when B is equal to 1, A copies and transfer to the output, and B is equal to 0, 0 copies and transfer to the output. Now first we discuss about the when both, that is control input, both will be 0, at that time data input is one is 0, another one is 1. That is at the same time the output will be, whatever input will be, A will be, suppose it is 0, here it is 1, the output will be 0. That is irrelevant of input, output will be same. So that is why I assign the value here as 0. So now it is 0, definitely the zeros will be transferred to the output. Next, when B is equal to 1, and here also B is equal to 1. Now see the data input. Here 0, what about the output? 0. Here it is 1, 1 will be output. That means whatever the data will be, just transfer to the output. Now I have to assign the A input as, I have to assign as A. So now B is equal to 1. Now this NMOS will be on. Whatever input will be copies, that is nothing but A will be copies and transfer to the output. So now what about here? B bar nothing but 0. So when it is 0, what happens? The 0 will be copies and transfer to the output. So this is about the, so this is nothing but a truth table of the AND gates. So by using a truth table AND gate, we have to design by using a pass transistor logic. Here number of transistors using pass transistor nothing but just only 2. So definitely we have to reduce the gates. So definitely the speed will be increases. Okay, this is the concept about the design of AND gate using pass transistor logic. Next, we will see about the NAND gate. So this is nothing but a truth table of the NAND gate, just opposite AND gate. So when both will be 0, output will be high, and either input will be high, another one is low, the output will be high, and A is high, output B will be low, output will be high, both will be high, output will be 0. That is nothing but Y is equal to A dot B the whole bar. Now we will familiar about this. When B is equal to 1, this NMOS will be on. When B is equal to 0, this NMOS will be on. Now we will check same as it is the pass transistor logic. We will see when first case, first combination, when A is equal to 0 and B is equal to 0, what about the output? Y is equal to 1. Next, same another control input, B is equal to 0. We will check the data input 1. Now what about the output? 1. Now here the control input both will be 0, the output will be 1, but whatever input in the data will be irrelevant of this. Then what happens? Definitely we have to assign the input as 1. So this is the case. When I am assigning this input as 1, whatever input will be the data input, the output will be 1. So here it is A is equal to 0, output will be 1. Here A is equal to 1, output will be 1. So now this is the B is nothing but the control input. A is nothing but the data input. Now next we have to see the control input 1. Now control input is 1. And another concept here is control input is 1. Now we will check. When A is equal to 0, what about the output? 1. And what about here? A is equal to 1, output will be 0. Now here data input 0, output will be 1. That is inverting. And here it is 1, output will be inverting, 0. Now we have to say that the data input is inverting value. That is why I assign this value data input nothing but A bar. Suppose A is equal to 1, the output will be 0. Suppose A is equal to 0, A is equal to 1, it will be 0. So opposite value is coming. So this is A, this is nothing but a B, and B bar is nothing but a control input, and this is nothing but a data input. Now when B is equal to 1, top transistor on, B is equal to 1, control input is 1, this NMOS will be on. This NMOS is on means whatever data will be copies and transfer to the output. Same as it is here, B is equal to 0, the bottom transistor on. So what happens? Whatever data input will be copies and transfer to the output. So now here this B is equal to 1, A bar copies and transfer to the output. And B is equal to 0, B is equal to 0, 1 copies and transfer to the output. So here also number of transistors will be reduced, only 2 transistors are using. So we have to reduce the power as well as the delay. Definitely the speed will be increases. Now we will see the next design of OR gate using pass transistor logic. So we are familiar about the OR gate equation, Y is equal to A plus B. So here there is the truth table of the OR gate. So here both will be 0, output will be 0. Any one of the input is high, output will be high. So this is the truth table of the OR gate. Now we will design the OR gate using a pass transistor logic. So this is B, and B bar is nothing but a control input, and there is a data input here. Now we will check here the concept. To design when B is equal to 0, what about the output? B is equal to 0, and again here also B is equal to 0. That means control inputs, so both will be 0. Here also 0, again here also 0. Now we will check the data input. data input here it will be 0. What about here? Here it will be 1. Now what about the output? Here it will be 0 and here it will be 1. So now when control input both will be 0, so we have to see that whatever data will be directly transferred to the output. That means 0 will be transferred to the output Y and here 1 will be transferred to the outputs. So now we have to assign, that is B bar control input, we have to assign the value as A. That means here I am assigning A. Suppose A is equal to 0 means that 0 will be transferred. Suppose A is equal to 1 means 1 will be transferred or copies will be transferred to the output Y. Now next we will see the another combination. Now we will see the control input 1. Here also the control input 1. Now we will see the data input. Here the data input is nothing but 0. So what about the output here? Here it is 1. What about here? Here it is 1. Here it is 1. Output will be 1. So that means irrelevant of data input, the output will be same. That means so control input is 1. When the case is control input is 1, then it is nothing but B here. So data input is 0 means 1 will be coming and here 1 means 1 will be coming. So that means you have to assign the high input at this data input here. So what happens when it is 1, what happens? B is equal to 1, this 1 will be transferred to the output. So here the B and B bar are nothing but the control input and this is nothing but A is the data input. So now here is mentioned here B is equal to 1, top transistors on and B is equal to 0, bottom transistor on. B is equal to nothing but B bar, bottom transistor on. Now B is equal to 1 copies and transfer to the output and B is equal to 0. B is equal to 0, A copies and transfer to the output. So here also we are using only 2 transistors. Pass transistors, this is NMOS transistors here. So just imagine that when you are using a CMOS circuits, we have to use PMOS as well as a NMOS. But here we are using pass transistor only single NMOS circuit is we are using. So number of transistors reduces and there is a leakage current also, reduction also reduces. So in case of using a CMOS, definitely a leakage current will be coming. So there is so many factors will be coming when you are using a CMOS circuit. But such a problem is not coming here for the pass transistors. Only transferring the data from input to output. So the equation is nothing but Y is equal to A plus B. Now we will see the next gate, NOR gate. So NOR gate using a pass transistor logic. See here, this is the truth table of the NOR gates. Just opposite, Y is equal to A plus B the whole bar. So now both. So the B is nothing but a control input. Now B is equal to 0. Here also B is equal to 0. So now we will check the data input. A is equal to 0, the output will be 1, and A is equal to 1, the output will be 0. So now here A is equal to data input is equal to 0, opposite of the input, and here data input is 1, opposite of the input. So now we have to assign the data as opposite. That is but A instead of A we have to assign A bar. So that is the concept behind this. So so B control input B is equal to 0 and control input B is equal to 0. When 0, what about the output? 1. Here it will be 0. So now I have to assign, it will be A bar, A whole bar. So now B bar is nothing but 0. So this NMOS transistor on. Once NMOS transistor is on, whatever input in the data will be transferred through this, will get the output. Now we will see the when control input is equal to 1, here it is 1 and here it is 1, both will be 1. Now we will see the data input. When it is data input is equal to 0, what about the output? Here it will be 0 and the data input is 1, here it will be 0. Now understand the concept here. Now control input both will be high state, but data input is irrelevant, but output will be same. So now we have to assign the value as the data input as the 0. Then only whatever input will be, when you are assigning this B is equal to high input, this 0 will be transferred to the output. So that is why here the table says. So now when it is both will be 0, what about the control input? A bar. When both will be 1, here data input is 0, output will be 0. Data input 1, output will be 0. That is irrelevant of the input, output will be same. That is the concept. That is why I assign the value as 0 at the data input here. So now B is equal to 1. So this 0 will be transposed and will get the output y is equal to a plus b the whole bar. Now the 4 possible combination we have to assign this B pass transistor logic. So here I am explaining B is equal to 1, top transistors on, and B is equal to 0, bottom transistor on. When B is equal to 1, that is nothing but 0 copies and transfer to the output. B is equal to 0, A copies, A bar, not A bar copies and transfer to the output. So this is the logic. So by using the truth table, that is nothing but NOR gate truth table, you have to design a pass transistor logic. By using a NOR gate truth table only we have to design a pass transistor logic. Then only we have to know here only we have to know the control input as well as the data input. So we consider B as the control input. That is why we have to assign here as B bar and assign here as the B. So now this is the concept behind the NOR gate using the pass transistor logic. So next we have to use the XOR gate. Design of XOR gate using a pass transistor logic. We are familiar about the XOR gate truth table. This is the XOR gate truth table. So now when it is a different input, A and B is different, output will be high. See here, the A is equal to 0 and B is equal to 1, output will be high. What about here? A is equal to 1, B is equal to 0, output will be high. So these two cases, the output will be high. When seeing this first combination, that's first cases, when both will be 0, A is equal to 0, B is equal to 0, what about the output? Y is equal to 0. And when both will be A and B, both will be high state, what will be the output? Output will be 0. So this is familiar about the XOR truth table. We are familiar about this XOR truth table. So by using this truth table, we have to design a pass transistor logic. So that is nothing but design of XOR gate using pass transistor logics. So now we will see the first case when B is equal to 0 here and another combination B is equal to 0, or we have to say it is a B bar. So when B is equal to 0, check the data input, A is equal to 0, what about the output? Y is equal to 0. And here B is equal to 0, check the data input, here it is 1 will be transferred. So what does that actually mean? When the whatever input or data input will be directly transposed to the output if the condition is nothing but, that is the control input will be B bar. So we have to say it is when B is equal to 0, whatever input in the data will be directly transferred. See the first case, when A is equal to 0, the 0 will be transferred here, and here it is control input is 0, 1 will be transferred here. So that is the concept. Now next we have to see the 1. When control input is equal to 1 and here also control input is equal to 1. When A is equal to 0, the output will be 1 and A is equal to 1, output will be 0. So what does actually mean? When control input is 1 or control input is high state, the whatever input will be inverting. If it is a 0, the 1 will be inverting. If it is 1, the 0 will be inverting. That is the concept behind the XOR gate. So now we will design a XOR gate circuit. So this is nothing but a B control input. Here it is a B bar. Now we have to see the first case when B is equal to 0. What about the input? A is equal to 0, output will be 0, and A is equal to 1, output will be 1. So this is nothing but a B bar. So now here I have to assign the A. Whatever input will be A, output will be transposed. That is nothing but A copies and transfer to the output. So that is nothing but Y is equal to A XOR B. Now next second case when both will be high. B is equal to high and B is equal to another case B is equal to high. Now check the input. A is equal to 0, 1 will be transposed 1, A If it is 1 means 0 will be transferred. So that is why here it is A bar. So A bar means here it is 0 means 1, and if it is 1 means 0. So that is why here it is. This is B is nothing but a control input. B is nothing but a control input. A bar is nothing but, if it is 0, output will be 1. If it is 0, output will be 1. If it is 1, the output will be 0. So that is the concept of the design of XOR gate using pass transistor logic. So here also we are using the only 2 transistors. Now see the when B is equal to 1, top transistor on. When B is equal to 0, bottom transistor on. When B is equal to 1, A bar copies, then nothing but transfers to the output. When B is equal to 0, A copies and transfer to the output. This is about the XOR gate using a pass transistor logic. Next, nothing but a design of XOR gate using a pass transistor logic. So now we are familiar about the logic gates. This is nothing but XOR gate truth table. The XOR gate truth table, we are familiar about that when both inputs are high as well as both inputs are low, the output will be high. The first case, see, it is a first case when A is equal to 0 and B is equal to 0, output will be 1. Same as it is here, when A is equal to 1, B is equal to 1, output will be high. So now we know that both will be, that is A and B will be same state, or we have to say it is low state. Output will be high. Here also when A and B will be same state. Same state means that A will be high as well as B will be high. And this both will be high, output will be definitely high. That is why here it is Y is equal to XOR of B the whole bar. Now we will check the conditions. Control input B. So here it is 0. What happens? We will check the data input. When it is 0, A is equal to 0. What about the output? 1. Now here again you check the output, control input. Here it is 0. Check the data input 1. It will be 0. That means 0 means 1 and 1 means 0. That means inverting. So now if it is a control input is nothing but low. Control input is low. When whatever input in the A will be or data input will be inverting. If it is low means output will be high, high means output will be low. See first case, when control input is 0, when A is 0, it will be inverting 1. Here in this case the control input is 0, here it is data input is 1, output will be inverting. Now we will see here. So here it is here B bar. Now I am assigning the value as A bar. When A is equal to 0, 1 will be transferred to the output. When A is equal to 0, 0 will be transferred to the output provided B input is equal to B bar is, or B is equal to 0. That is why here I am assigned as B bar. Next we have to check the value as when control input is equal to 1 and here also control input is equal to 1. When what about this is the data value? Data is nothing but 0, the output will be 0. And here data will be 1 will be transferred. That means what does actually mean when whatever the data input will be transfers. That is whether A is 0 means 0 will be transferred, then 1 means 1 will be transfers provided the control input is equal to high. So here it is, this is the control input B, here it is high. When A is equal to 0, the output will be 0. When A is equal to 1, 1 will be transferred. So this is about the design of XOR gate using a pass transistor logic. So by using this pass transistor logic, you have to reduce number of transistors and you have to decrease the delay as well as improve the speed as well as the less power consumption. So now B is equal to 1, top transistor on, and B is equal to 0, bottom transistor on. B is equal to 1. A copies and transfer to the output. When B is equal to 0, A bar copies and transfer to the output. So by using a XOR truth table, we have to design a pass transistor. So pass transistor nothing but a transiting the information from data input to output. So by using a single transistor, we have to transfer the output. We have to reduce the number of transistors. So compare other logic, pass transistor will be less number of transistors using in the VLSI circuits. Next, so design of 2:1 mux using the pass transistor logic. Now Here we have to use the input as A and B. There is a selection input S and S bar. So when S is equal to 0, this is equal to 0, A will be selected. When S is equal to 1, B will be selected. So when S is equal to 0, A copies and transfer to the output. When S is equal to 1, B copies and transfer to the output. The equation is nothing but Z is equal to A dot S bar plus B dot S. So design of 2:1 multiplexer. So what is multiplexer? Multiplexer nothing but a data selector. It will select the data. So whatever data we need, by using a selection input, based on the selection input, we have to select whether A or B. If selection input is 0, A will be selected. Suppose selection input is 1, B will be selected. That is the concept behind this. Suppose S bar is the selection. S is nothing but a selection input. When S is equal to 0, this transistor on, NMOS transistor on. When this the NMOS transistor on, whatever input, data input will be transferred to the output. That is why I wrote in equation Z is equal to A dot S bar. When S is equal to 1, what happens? Here this NMOS will be on. Simultaneously, what about this? This NMOS will be off. So what happened? This NMOS will be on. This will be off. Now whatever input B will be transfers through the switch. So this is the concept behind the 2:1 multiplexer by using a pass transfer logic. So by using a pass transfer logic, designing a 2:1 multiplexer, number of transistors will be less. When the number of transistors less, definitely power consumption is less and speed will be definitely increases. That is the concept behind this. Here it is 0, A copies and transfer to the output. When S is equal to 1, B copies and transfer to the output. So next we have to see the design of AND gate using a transmission gate logic. Now here there is a transmission gate. So we are familiar about the gates, AND gate, OR gate, NOR, XNOR, and so by using the gates, by using a design of a transmission gate using logic gates, when we are here the concept is nothing but both is PMOS as well as NMOS are combined together. Both PMOS as well as NMOS are combined together. Now same concept we are designing the AND gate, but previous case it is single transition. Here it is a double transition, nothing but PMOS as well as NMOS. So what is the difference between the previous case as well as the transmission gate? Nothing but previous case is nothing but output voltage or voltage strength is nothing but somewhat less compared with the transmission gate. So transmission gate is nothing but a bidirectional switching. So here when we are giving them input or control input, what happens? So simultaneously both will be conducting. So what when you are conducting both the same transistor will be on. So voltage strength will be very high. So definitely the circuit having a proper voltage. So it will not be less voltage strength. That is the concept behind this transmission gate. Now we will see the AND gate. So this is the truth table of the AND gate. When both inputs are low, output will be low. When A is low, B is high, output will be low. When A is equal to high and B is equal to low, output will be low. When both will be high, output will be high. Output will be high. Now see the lesson point. Okay. Now so now any one of the input is low, definitely output will be high. Now see the I have to design. See the first case, the control B is control input, A is the data input. When B is equal to 0, at the same time what about the input A is equal to 0, output will be 1. Another case, here it is B is equal to 0, at the same time what about the data input 1, output will be 1. So whatever data irrelevant of the input, output will be same. That is a concept. When A is equal to 0, output will be high. When A is equal to 1, output will be high. The condition is when both will be this the control input. When B is equal to 0, here also B is equal to 0. Now we apply here when B is equal to 0. So here when b is equal to 0, b is equal to 0, so what about here? This p bar means 1. So this transmission gate will be on, 1 will be transferred to the output. So whatever control input, that is nothing but when control input is 0, so what happens? The input, data input 1 will be transferred to the output. So next we will see the control input is 1 and here also control input is 1. See the data input, here A is equal to 0, here A is equal to 1. A is equal to 0, what is the output? 1, and A is equal to 1, output will be 0. That means whatever the input, the output will be just opposite to that. That means we have to assign A bar. See now, when B is equal to 1 and here also B is equal to 1, the A is equal to data input is 0, but output will be inverting 1. But here also 1, the output will be 0 inverting. So now that is why I have to assign A bar. Now B is equal to 1. What about this transmission gate on and this also on? So both will be simultaneously on. When both will be simultaneously on, whatever input will be, data input will be transmitted simultaneously. The both PMOS as well as the NMOS will be on. So definitely there is a voltage turn, high voltage turn. So it have to the output will be Y is equal to A dot B the whole power. So this is the concept behind this NAND gate. Now B is equal to 0, 1 copies and transfer to the output, and B is equal to 1, A bar copies and transfer to the output. So next we have to see the OR gate using a transmission gate. So last time we see same as it is truth table. So both will be 0, output will be 0. Any one of the input is high, definitely the output will be high. Now we have to design. Before designing, first we have to check the control input when both will be 0. When control input both will be 0. The first combination, that is when B is equal to 0, check the data input 0, output will be same. And here again we will check when B is equal to 0, check the data input 1, the output will be 1. Then when the control input is equal to 0, whatever input will be just transfers or copies transfer to the output. If it is A means 0 means 0 will be transfers. If it is 1 means 1 will be transfers. That is why here I connect here. This is the transmission gate. Now B is equal to 0. What happens? Nothing but this A will be copies and transfer to the output. So B means 0 means this PMOS will be on, simultaneously this NMOS will be on. So both will be on simultaneously. This transmission gate will be enabled, and this enabled transmission gate will be transfers A from data input to output. So next we will see the control input 1. When B is equal to 1 and here also B is equal to 1. Now what about check the data input? When data input is equal to 0, output will be 1, and here data input is equal to B, that is control input is equal to 1, data input is 1, output will be 1. So that means when control input both will be 1, the output will be different. That means it will not follow the input. So either irrelevant of the input, so output will be same. That means 1. That is why I assign the output as input as 1. Now when both will be 1, when B is equal to 1 means here it is 0, this PMOS on. When B is equal to 1 means this NMOS will be on. Both will be enabled. If both will be enabled, whatever data input will be transposed to the transmission gate and will get the output. So that is nothing but a OR gate. So when B is equal to 0, A copies and transfer to the output, and B is equal to 1, 1 copies and transfer to the output. So this is the concept of the design of OR gate using transmission gate logic. So by using a control input and data input, we have to transfer the data from input to output. So here number of transfers is comparatively more compared with the fast transfer logic, but the advantage nothing but the number of that is voltage strength is high compared with the fast transfer logic. In fast transfer logic, the voltage strength is weak. In case of a transmission logic, the voltage strength is strong. That is the concept difference between the fast transfer as well as the transmission gate logics. Next, we have to see the NOR gate. So this is the NOR gate truth table. So NOR gate truth table, there is a 2 input NOR gate truth table. there is a 4 possible combination 0 0 0 1 1 0 1 1 combination. Now I have to check same concept when the control input is both will be 0. Control input both means here it will be 0, here it will be 0. Now check the data value. Data value is nothing but A is equal to 0. What is the output? 1. And what about here? This data value is equal to 1, output will be 0. That means, so when control input both will be 0, the whatever data will be inverted at the output. That is the concept behind this. Now A is equal to 0 means 1 will be reflected and 1 means 0 will be reflected. That is the concept. So now I have to assign this transistor gate data input as A bar. When A is equal to 0, that means 1 will be transferred to the output. When A is equal to 0 means 1 will be transferred to the output. So now B is equal to 0 means, so both this transistor, this PMOS as well as NMOS will be on. Now we move on to control input is equal to 1. So here it is 1 and here it is 1. Now check the data value, data input. So data input is equal to here 0, output will be 0. And data input is equal to 1, output will be 0. Then what does that actually means? Whatever data input, the output will be same. That means nothing but different from the data input. That is the concept. So here 0, the output will be 0. Here it is 1, it will be 0. That means I have to assign the data input as 0 and the control input is nothing but both will be high. When it is B is equal to high, this NMOS transistor will be on. This NMOS transistor on, definitely this 0 will be passing, and B is equal to B bar is equal to 1, it means 0, that is PMOS will be enabled. So PMOS unit is enabled, when it is 0 it will be enabled, when B is equal to 1 this NMOS will be enabled. So simultaneously it is a bidirectional switch, so both will be simultaneously conducting the data input to the output. That is why we have to say a strong voltage will be passing from data, that is input to output. That is why we are advantages of the transmission gate. So by using a transmission gate, we have to design a NOR gate. So here this is the output, y is equal to a plus b the whole bar. When b is equal to 0, a bar copies, this is nothing but a bar copies transfer to the output. When b is equal to 1, 0 copies and transfer to the output. So this is about the NOR gate using a transmission gate. So by using a truth table only, we have to design a transmission gate logic. So here the drawback is nothing but number of transistors increases. That is the main drawback. And next we will see the XNOR gate. We are familiar about these equations. Last we will be using the pass transistor logic. We have to see when both inputs are low, output will be high, and both inputs are high, output will be low. Output will be high. When the A and B both will be same state, output will be high. That means both will be 0, output will be high, and both will be 1, output will be high. Remaining state, output will be low. That is whether A will be low or B will be high, or A will be high, B will be low, the output will be 0. Now using a Boston's XNOR gate truth table, we have to design the transmission gate logic. Now we will see the conditions as it is. This B is nothing but a control input. Here it is 0. Now B is equal to 0 and here also B is equal to 0. This is nothing but control input. Now check the data input A. Here it is 0. What about the output? 1. Here also 0. What about the output? 1. Here data input is 1. Output will be 0. That means when data input is 0, output will be 1. When data input is 1, output will be 0. That means the input will be inverting. That is the concept. When the control input is low state, whatever data will be inverted at the output. That is the concept behind this. So now what I can see there, when we are designing a circuit, here it is this is the B bar, nothing but when B is equal to 0, this NMOS will be on. When B is equal to 0 means this PMOS will be on. Here A bar means 1 means 0 will be transferred, 0 means 1 will be transferred. That is the concept is nothing but y is equal to A XOR B the whole bar. Now next condition, control input is equal to 1. Here also control input is equal to 1. Now check the data input. Data input is equal to A is equal to 0. Output is equal to 0. Now check the here A is equal to 1. Output will be 1. That means when control input is equal to high, whatever data input will be directly reflected at the output. That is the concept behind this. Now control input is high, 0 will be transferred to the output. Here control input is at high, 1 will be transferred to the output. That is why here I am designing the transmission gate when A is equal to, when A input data input is equal to A, when B is equal to 1, this NMOS will be on, and B bar is equal to 0, the B bar is equal to 1, that means 0, this PMOS will be on. This PMOS as well as NMOS simultaneously on. This is nothing but a bidirectional switching. So both will be transposed A input to the output of the circuits. That is why here I am mentioning when B is equal to 0, A copies and transfer to the output. When B is equal to 1, A copies and transfer to the output. So this is about the XNOR gate by using a transmission gate. Next, design of XOR gate using a transmission gate logic. Now, same as it is a truth table, it is a 2 input XOR gate. There is 0 0 and 0 1, 1 0, 1 1. When 0 0 combination, output will be 0, 0 1 combination, output will be 1, 1 0 combination, output will be 1, and both will be high, output will be 0. That means, and when we are designing XOR gate or XOR gate truth table, we are able to understand that when it is different input, definitely we have to say output will be high. In previous case, XNOR gate, when the both inputs will be low, output will be high. Both input will be same state, but when both input will be same state, output will be high. That means in XNOR gate, A is equal to 0, B is equal to 0, output will be high, and A is equal to 1 and B is equal to 1, output will be high. But in case of XOR gate, when it is a different state, when it is a different state, output will be 1, and here also it is a different state, output will be 1. Remaining state, that means A both will be low or A and B both will be high, output will be low. So by using the concept, we have to design a circuits. Now we will see the first case, control input is equal to 0. Here it is 0 and here it is 0. Now check the condition. Here it is 0, when you can see it 0, check the data value. Here data value is equal to 0, the output will be 0. And what about here? Here data value is equal to 0, the output input is equal to 1, 1 will be transferred. That means actually what does mean when control input is equal to low, so whatever data input will be directly appear at the output. That means simply A copies to the or transfer to the output. When B is equal to control input, B is equal to low, here also low, whatever input will be directly transferred to the output or reflected at the output. 1 will be reflected at the output. So now see here, we are designing the XOR gate. Here it is a B bar, means in 0. So this what happens? Here it is 0 means here it is 0 means 1. Here it is 0 means this PMOS on. So this PMOS as well as simultaneous NMOS on. Whatever input A will be directly transfers at the output. And next the control input is equal to high. Here also control input is equal to high. Now check the data input. When data input is equal to 0, what about the output is equal to 1. Now data input is equal to 1, output will be 0. Now what does it mean actually? When the control input is high, whatever data input will be the just opposite or mean inverted. That means inverted. And 0 means 1 will be inverted, and 1 means 0 will be inverted. So that is the concept behind this. So when the control input is equal to high, A0 will be inverted at 1, and when control input is equal to 1 will be inverted at the output is 0. So by using this case, here it will be a B. When B is equal to 1, this NMOS will be on, and B bar is equal to 1 means here it is 0, this PMOS will be on. That is transmission gate, nothing but combination of PMOS as well as NMOS gates. So both will be combined together, will be say nothing but a transmission gate. Now here it is A bar. A bar means here it is A is equal to 0 means 1 will be transposed. A is equal to 0 means 1. If it is 1 means 0 will be transposed. So based on the truth table, we have to design a XNOR gate using a transmission gate. So here it is a B is a control input and A is a data input. Now B is equal to 0, A copies, transfer to the output, and B is equal to 1, A bar copies and transfer to the output. Next, design of 2:1 multiplexer using a transmission gate logic. Now we will see the 2:1 multiplexer. Multiplexer is nothing but a data selector. So whenever we need some selection of data or some applications we need selecting a data, by using a multiplexer we have to select. So here we are using a transmission gate logic using this 2:1 mux. So now this is the transmission gate 1 and here it is 2. Now here when this is equal to 0, what happens? This NMOS will be on. When this is equal to 0 means here it is 0. Here it is when this is equal to 0 means this NMOS will be off, and what about this PMOS will be off. Now we will see here when this is equal to 0. So this is equal to 0 means this this is equal to 0 means here it will be 1. This NMOS on. What about here? This is equal to 1 means this PMOS will be on. So B will be transposed to the output. That is nothing but B dot S bar. And S is equal to 1. This NMOS will be on. 1 means here it will be 0. This PMOS will be on. Whatever input A will be transposed to the output. That is why I wrote the equation EAZ is equal to A dot S plus B dot S bar. So it will be select. Suppose S is nothing but a selector input. S is nothing but a selector input. If it is 0 means it will be, if it is a 0 means it is B will be selected, and it is 1 means A will be selected. Okay. So by using this concept you have to design a mux. So this is nothing, so here number of transistors is nothing but a 2 transistor gate, but 2 transistor gate is nothing but 4 number of transistors. So this one set is nothing but a 2 transistors, PMOS as well as NMOS. Here also nothing but a PMOS as well as NMOS transistor, and the equation nothing but Z is equal to A dot S plus P dot S bar. So where the output is nothing but S is equal to 0, is equal to 0, what happens? Nothing but, so here it is P copies and transfer to the output. When S is equal to 0, this P copies and transfer to the output. When S is equal to 0 means here it is 1. This NMOS on as well as PMOS on. So this simultaneously both will be on, nothing but a bidirectional switch. This will be transferring the P output to the Y, Z. And next, when S is equal to 1, here it is 1 when this NMOS on, and what about it? This will be 0. A copies and transfer to the output. When Z is equal to Z is equal to A dot S plus P dot S bar. So S is equal to 0. P copies and transfer to the output. When S is equal to 1, A copies and transfer to the output. So by using this transmission gate, we are using the NMOS transistors. So this is about my topic lecture. Thank you all.